Okay, so these are the learning goals for today. So we will talk about an overview of the rendering pipeline. We will talk about geometric primitives, the geometric primitives that we use to send information to the pipeline, to the GPU. We'll talk about voxels because a lot of people were asking about that, and it's very important. And I didn't have, I was not planning to cover the topic right now, but I think because you ask, it is super relevant. And yeah, so I will explain this confusing thing about the voxels. And we will talk about what we in computer graphics call the scene. And we will have a very quick overview of the vertex shader, the tessellation shader, and the geometry shader. These are stages in the in the rendering pipeline. So, as we said, the rendering process is like a tiny factory, right? And as any factory, imagine that it's a factory that made cards. You need to put things inside that factory, so, right? So you have an input and an output, and inside that factory, imagine that you have like a conveyor, and you could have different stages inside that factory, right? So maybe you have like all the metal and like wheels and a lot of supplies, right, to create this car. And inside, in different stages, there can be robots and people and many things, creating step by step what in the end is a car. In this case, instead of creating a car, we will just create an image, right? So we will have geometry information. That will be the input. And inside, there are a lot of stages that we will study today. And outside, we will have a 2D pixelated image. So this is how the interior of this factory kind of looks. And give me a second because I need to put the chat somewhere that is not. Okay, great. I found a convenient place to put the chat. So this is what is inside the factory, right? So as if you follow the arrows, right? This is where we fit all the information we have, and there are sorry. So this is basically the pipeline, right? So in every stage we perform different things to the data. Okay, and in particular, the stages are super important for us and for this computer graphics course are the vertex shader and the fragment shader. Okay, basically the rest of the stages are fixed in the GPU or fixed in the rendering pipeline. Those, the vertex shader and the fragment shader, are the only ones that you can actually program. You can also play a little bit with the geometry shader. I will explain that later, but those are like the main important ones, right? So today it will be like a quick overview of the rendering pipeline, and tomorrow we will like finish that part, and then we will have like a lot of information about the vertex shader, then a lot of information about the fragment shader, because those are the main things that you will use. Okay, so basically the information is like going through these sections. So first is the vertex shader, then we have the tessellation section with the geometry shader. Then all this section is called rasterization or rasterizing. This is where the geometric information that we feed to the GPU is basically converted in something called fragments. Fragments are similar to pixels. They're not pixels yet, but in the end is similar to pixels. And then is the fragment shader that in the end decides those fragments, how they look really into pixels, and then we just create a pixel. Okay, and again we will explain all these things deep. Okay, so let's first talk about what we need to put inside the pipeline. So everything that we do before the rendering pipeline, before sending information to the GPU, it is usually called the application stage. So the application stage is it could be, for example, what you do in a software like 3 Studio Max or Maya or Blender, or it could also be the part of the code that you will do in JavaScript. So a lot of the things that you will do in JavaScript before calling your vertex shader, that is basically creating your geometry and defining that there's a sphere here and there's a plane in this other side and defining the materials, all that stuff. That is the application stage. Okay, so we will talk about first. We'll talk about the primitives, and might be the smoke. Yes, yes. If you don't know, we have a lot of problems right now in British Columbia, and yeah, the smoke is very bad. It's not JavaScript. Okay, great. So say yes if you can hear me perfect, and there was no problem with. Great, perfect. Okay, so let's talk about graphics primitives. So the graphics primitives are this. These are the objects, the geometric objects or geometric entities that can be understood by the GPU. So the GPU, they don't understand anything but points, lines, and triangles, right? And when we say about points, we refer to a type of data that we already talked in the math review, for those who haven't seen, that is what we usually call vectors, right? So it's basically a tree tuple of three real numbers, right? So in the end, a point represents a position, right? And it has a vector associated with that. So the graphics pipeline, again, they only understand points, lines, and triangles. And those are the entities that they can render, right? Those are the entities that can be converted into pixels. And with only those three things, we can create whatever we want, right? Like super, like creative stuff. So the thing is, you will see in many books, you will see the complete list of OpenGL primitives. It has actually 10 primitives. The thing is, these are the real primitives, and the rest are kind of extended graphics primitives. So what are those? In the case of lines, right? So for example, in this case, the line is like a segment, right? And it has two entities, two positions or 2 points, right? The extended version are this, a line strip and a line loop. This, in the end, is the same concept with just a different data structure. So imagine that we use a data structure of single lines to represent this line strip. We will basically duplicate information, right? Because for the first segment, we will have vertex 0 and vertex 1. And then for the second segment, we will need to store vertex 1 again, and then vertex 2. For the third one, we will need to store vertex 2 again, and then vertex 3. So in the end, they are just duplicating, right? So these are just different data structures in which, in the case of line strip, it's just a sequential, a sequence of vertex numbers, right? And the computer or the GPU understands, or OpenGL understands that what you want is a sequence of segments, right? So this is just only created by to save data, right? Same with line loop. The only difference between these two is that line loop assumes that there's a segment between the last point and the first one, right? And that's it. But in the end, they are composed by the real primitive that is a line, right? Same happens, or something similar happens with the extended graphics primitives with triangles, right? So the real primitive is the triangle, but you can create those triangles can be represented as a triangle strip, triangle fans, or can be represented also as quads or quad strips or polygons, right? Again, this is just a different data structure that is used to save space, right? Again, this is just to save duplicating information of what each triangle has, right? We will probably not have time to cover like all the type of data structure, the types of data structure that can be used in meshes, because that is covered in deep on Ala's course, the geometric modeling course. But there are different ways to represent meshes. So one, for example, is again with individual triangles, in which you have, for each triangle, you have 3 points associated. In this case, it will be will be duplicated, right? So yeah, it's only different type of data. These are a bit different, right? Because these do not have triangles, right? And we can do this. This is very common, specifically quads. These are very common with 3D models made by artists, or in the end made by humans. Um, for computers and for geometry processing, it's way better and is more convenient to have triangles, because most of the geometric processing algorithms work on triangles, and at the end the GPU only understands triangles. But from the human perspective, from an artist perspective, creating a 3D model using only triangles is very hard. So usually they use quads. I will show you a 3D model that is actually using quads, and you will see why it's better. And so in the end, the 3D model can have quads. The thing is that those quads are usually triangulated on the GPU in real time, right? Choosing the best triangulation. So it doesn't matter if you send a polygon to the GPU. In the end, the GPU will decide how to triangulate that polygon, and in the end, everything will be triangles, okay? And when I say choosing the best triangulation, this is usually related with the dihedral angle. So for example, in this case, I am choosing the shortest edge. That is something that it can be used as a rule if the quad is flat, for example. But sometimes the quads are not flat. So I will show you an example of this. Let me just switch. So here we have a 3D model. We are in 3 to the max. And here we have a 3D model that has a certain shape. And as you can see, these are quads. Okay, I made this model using quads. Okay, but it looks weird, right? It looks very weird, but it shouldn't be, right? The problem of this object is its triangulation, is the way the computer is triangulating. Usually the computer will choose, the graphics card will choose the best triangulation possible. In this case, I force the computer to choose exactly the opposite of the best triangulation. So that's why this looks weird. So I will show you what could be better. So I will copy this guy, and I will get this, and I will select polygons. I will select edit triangulation, and here we can see the triangulation that I forced the computer to create, right? So it looks weird. If I now say the computer, okay, no, instead of this triangulation, choose this one. If I just modify the way the triangles are created in those quads, now the shape looks better, right? And basically, geometrically speaking, this vertical triangulation, or these vertical edges, are those in which the dihedral angle between those two planes, or the dihedral angle between those two triangles, is more planar. Okay, so yeah, this starts to look better, right? I will not spend time fixing this other part, but I think for now you could understand what I mean when I said choose the best triangulation. Okay, so those type of things will be totally automatic in the GPU unless you change that, unless you say that is different. Okay, so these are the primitives again. So the GPU only understands triangles, points, and lines. So what happens with the voxels, right? Because you were asking about that. Okay, what is this? We have some. Can you see like an orange thing here? I don't know what is that. It's kind of weird. Okay, so what are voxels? So basically, oh, what is happening? Someone is drawing on top of our Zoom, and it's not me. Okay. Okay, someone is probably trolling. I don't know. I don't understand. Yeah, this is weird. Yeah, disable in Zoom. Whiteboard tools. Ah, okay. I didn't know that was possible. Sorry. Okay, we cannot waste time right now. I will see later how can I disable that. For now, if the the person that is doing that, please stop that. If you can erase it, please erase it. But I cannot waste time right now in fixing that. Okay, so let's talk about voxels. So with voxels, as we said, what you have is you have a volume, right? You have a space, and you discretize that space. You discretize that space in cubes, right? Let's pretend that for now we are seeing a cross section of that space, so we are seeing a 2D version of that. Okay. This will be very, very bad to have these things. So if you want to represent this a sphere, the 2D version of the sphere or the cross section will be a circle, right? So the shape you want to represent, it could be an implicit function, for example. It could be the implicit function of the sphere, or it could be whatever you want. You only need to know where is the inside and the outside of that shape, right? So once you have that, once you have some way algorithmically a way to understand what is the inside and the outside of this entire space, you can just understand that some voxels are inside and outside, right? And you can just turn on the voxels that are inside and turn off the ones that are outside, right? So in the end, this is the volume representation of your shape, right? And again, there is no geometry yet, right? So in this case, voxels, you can have, for example, a voxel class, right? And that class has, for each voxels, you can have information. So you'll have who are the neighbors of those voxels, what is the color of that voxel, obviously its position in the space, the materials. You can have a lot of things. Yeah, someone is already asking, how do you determine if points are inside or outside? Please keep your questions for the question break. Okay, and so once you have that, then you can have another rule to determine which voxels are not on the border, which voxels are really inside the shape. That is usually determined by counting the number of neighbors, right? So for example, if I check this voxel here, all its neighbors are turned on, right? It means that this guy is inside. If I check this one here, some of its neighbors are already gone, are already off, right? It means that you are surely on the border, right? So once you decide which are on the borders, right, then you can check which faces are only visible from only the voxels that are only in the border, right? And you can process all those faces and basically create triangles only on those faces. So in the end, you create a polygonal mesh, right? And that is what you send to the pipeline. So that's why, it is confusing. It's like the voxels per se, voxels are not polygonal meshes. But what you do with the voxel information you have at the application stage and the way you, and in the end, you need to create a polygonal mesh, right? And that is what you send to the pipeline, right? And that is actually a polygonal mesh. Good. Okay. Yes, this is driving me crazy. Let me check if I can just fix this. Sorry. How can I erase this? The eraser is not, damn, the eraser is not even activated. Okay, it's a shame. I mean, I hope it was by accident, because it's a shame, because otherwise I will need to basically record the video again. It will be a shame. Okay, so great. So those were the primitives, right? And again, it doesn't matter what are you representing. Someone says, can you reply what you said? in your some settings you can disable public annotation. Yes, guys, but the thing is, right now I don't want to spend time. Chat. Show names of annotations. Disable participant annotation. Okay, maybe it's here. Okay. It says show names of annotations. That means that we can know who was the person who did this. Now again, I am assuming that it was by accident. Hiding by half load and share computer sound optimize share. But I wanted to erase this thing. Ah, damn. Okay, doesn't matter. Okay, so those are the primitives. Okay, now let's talk about the scene. So what is the scene? So the scene is just a little bit more information rather than only the one from geometry. So we also have coordinate frames, obviously the 3D models, basically the geometry. We can also have the materials and lights information and camera. Okay, so I will switch to 3 to the max to show you what is that. Okay, good. So here's an example of a scene in 3 to the max. Okay, and so we have models. We have the 3D models of this tiny car, and we have a camera. Okay, it has something very interesting that has this like conic shape. We usually call this conic shape, we call it frustum, and we will talk about that. And there are a lot of math involved and matrices involved in like creating this frustum. And each of these objects here is a different 3D model. And because it's a different 3D model, it has its own coordinate frames. So as you can see, if I select these objects here, each object has its own coordinate frames. It's X, Y, and Z. It's basis vectors, which mean that it has a matrix that is representing its coordinates, its object coordinates. Okay, but all those objects need to be assembled in a world, in a 3D world, right? What I'm saying is, if you create an OBJ file, a 3D model file for each of these shapes, and you open those shapes in a different program, for example, you will see that they will be like this section here will be like centered on the 0, 0, 0 of the Euclidean 3D space. But in your scene, you need to move your stuff, right? You need to move the wheels to be exactly on the correct place in the end, like creating the entire shape, right? The entire scene. So there are coordinate frames for the models for each object, and there is also a single world coordinate frame for the entire scene. And there are some matrices that we will use to convert from the model coordinate frame to the world coordinate frame. And then we have another matrix, and we will create other matrices to convert from the world coordinate frame to the perspective camera. Okay, and then from the perspective camera to the screen camera. Sorry, to the screen coordinates. So there are a lot of matrices involved. Again, I'm not going deep right now because we will cover that on one of the lectures. But now I just want you to visualize this. For example, the coordinate frame of this wheel. If I say 3 to the max to show me the local coordinate frame, this is rotated, for example, right? So it is obviously very different to the coordinate frame, to the local coordinate frame of this object, right? This is already rotated. But in the end, they all live in a world in which we have a camera, and we have lights, and we have materials, and we have many things, right? So 3 to the max is a very complex software, and again, I can create 3D models and a lot of stuff inside 3 to the max, and the goal is to create all this data that we can send to the graphics pipeline. The only part that is not created directly by 3 to the max is actually the viewport. So the representation of my objects that I'm seeing here right now in the viewport is not created by Trees to the Max, but it's actually created by OpenGL. Okay, so Trees to the Max is right now sending all that information, all those primitives and everything to OpenGL, and OpenGL is basically painting all these pixels, right? I have different views. I have another view here in which I am seeing the actual final render as it's seen from this camera, right? All already with lights and materials. And again, this is rendered in OpenGL. Okay, good. So let's take a quick break for taking notes and questions. Now it's time for questions. Let's see. Okay, someone was asking about like how can you know what is inside and what is outside. Depends on the geometry that you want to represent. So for example, there are can you go over what you said about voxels again? Yes, for sure. Everything? Do you need, can we think? Can we think line loop is a closed line strip? Yes, that is exactly what it is. Line loop is a closed line strip. Basically, it's just like the computer will create a final segment to close from the end to the beginning. Okay, so let me just come back to the presentation. And you want me to explain. Okay, so do you need for me to explain entirely the voxels again? Please say yes if you need. Okay, no one is saying yes. Okay, but you were asking about just the part of the boundary. Okay, great. So the part of the boundary. So we have this boundary, right? This is right now it's in 2D. It's a 2D representation, like a cross section of the sphere. But let's imagine that it's a sphere. The thing is, there are different ways in which you can represent geometries using math, right? So one is, for example, using implicit function. An implicit function is a function that will tell you, it will give you a negative value on one side of the equation, a positive value outside of the equation, and a zero on exactly the border of the equation, right? So basically, in this case, you could use the implicit version of a circle or the implicit version of a sphere and use the position of those voxels. You feed those positions into that function, into that implicit function, and it will tell you if it's inside or outside depending on the sign of the result. That is one option, okay? If you want to represent something that it was originally a mesh, right? So imagine that instead of representing a circle, you want to represent the Stanford bunny or a dragon, right? That is totally different because there is, I mean, it will be very hard. It is possible, but it is very hard to have like a function, an implicit function that describes a dragon, right? That is crazy. So that is something different. That is actually so hard that there is a lot of research involved on that. So taking an object, a mesh, for example, or pieces of a mesh or a point cloud, and computing what is inside or outside that is a research topic in geometry processing. There are a lot of papers regarding that. Yeah, so it is complicated. So for example, sometimes what you can do is you can take your mesh, again, let's imagine the dragon, so you can take the mesh and you can simplify the mesh with different geometric processing algorithms. You can simplify the mesh and transform your mesh in like groups of primitive shapes like spheres and boxes and things like that. And you can use that information to actually compute the inside or outside. And another way to do it that is probably the easiest is to compute something like a software reconstruction using Poisson. So Poisson reconstruction is an algorithm that is usually the intention of that algorithm is to take a point cloud and basically reconstruct a shape out of that point cloud. I will show you something very quickly, actually. In a second. Give me a second. So this is another software. This is called MeshLab. This is a software that we use a lot in geometry processing. And let me just hide this. This is an example of the type of information that I had, for example, in my VR project, right? In my VR reconstruction project. I wanted to show you this because it's an example of information that comes in the shape of polylines, right? Or these line strips or segment strips. So this is the information I was getting from the users that were doing VR drawing, right? So inside my application, my own application that I created in C++, this is the only information I had. I had positions of all those vertices in 3D, so I could create or recreate those strokes, and for all those points I had also information about its normals. Okay, and I will explain what a normal is. And so in the end, this can be also seen as a point cloud, right? So I can show the points in a more evident way. So these are all the points of this object. Okay, so what I mean with Poisson reconstruction, I can go here, for example, and go filters, meshing, and use this Poisson reconstruction, apply. Forget it. I cannot use with this file in particular. Okay, I promise I will show you Poisson reconstruction next lecture for you to try to understand what I mean with this inside outside. Okay, but yeah, I wanted to show you this because this is an example of how can you the way you can have information that is actually not triangles, right? And let me show you what we used to render. So again, this is the geometrical information we had, and this is the renders we were creating, right? So when we were at our application stage, we were creating quads and then sending quads to the pipeline, right? So that is in the end what happens with voxels, right? You can have information about the volume and your voxels, and you have, again, you can have a class that is defining the voxel, and you can have a huge array with all your voxels, right? But you will not send like millions of cubes to the rendering pipeline. You only send the ones that are outside the border. Okay, so yeah, new questions, please. Okay, you keep talking about the boundary. Is there any other question? Any new question? Okay. Apparently there are no more questions. So what is exactly the input that is sent? Okay, the input that is sent to the graphics pipeline, again, triangles, either triangles, vertex, or lines, right? It is similar to Minecraft. Yes, exactly. That is exactly what happens to Minecraft. Minecraft, the render engine from Minecraft has information of all the voxels, but in the end, in real time, is creating a mesh that is only the outside of the mesh, that is like sending to the graphics pipeline. Local coordinate system is the model coordinate system. Yes, local coordinate system is the model coordinate system in Tristan Max. Yes, is voxel like points? Yes, actually, in some sense, yes. Again, voxels, what you usually will have is you can have a class, right, and a class voxel, and for a class voxel you probably need its position, right, and its position can be either literally a vector, like three real numbers with a position, or because at the end this is a discretized, right? It's a discretized space. Instead of having three real numbers, you could have three integers, because at the end you only need to know like which position in this space is occupied by this voxel, right? But yeah, in the end, a voxel is kind of representing a position in space, and depends on the shape of that voxel, you can define many things. 3D pixel, more like, exactly. A voxel is basically a 3 pixel. Voxel 3 pixel. Okay, perfect. So I think we have enough information already about voxels. Again, if there is something that you don't understand, please go and you can go to Piazza and put more questions if you think you need. Okay. So let me just come back. Okay. Yeah, and we're almost done. Okay, so we already talked about primitives, and we already talked about scenes. So now let me tell you a very quick overview of what are the next sections. Okay, so now the next section is the vertex shader. Okay, so the vertex shader executes one time per triangle, okay, or one time per point, or one time per lines, right? Remember, the primitives are triangles, lines, or points. So vertex shader, it will execute one time per primitives, okay? And there are two main goals of a vertex shader. So the first one is to compute the screen position of each vertex, and it does that by composing different transformation matrices. Again, we will do that, and we will see all the math that is involved there, but the one that is actually doing that like composing those transformation matrices, is the vertex shader. And it also needs to evaluate any vertex output data that we want, like, for example, the normals. And also the modern vertex shader right now is very cool, because you can actually animate the vertices. And that is exactly what you need to do on your assignment. So remember, you will start attend your labs in this week, and you will start like playing with that. And that is something that you will do on your first assignment. You will take your vertex shader, and you will tell the computer to move the vertices not at the application stage, but already on the GPU. Okay. So quickly, do you know? Please say no if you don't know what the normal is. No. Great. Okay. So many people don't know what a normal is. Perfect. So let me just, again, quickly jump to 3 to the max to show you what a normal is. So basically the normal is the direction, it's a perpendicular direction, or a direction that is perpendicular, sorry, to a surface, okay? So I think the best way for me to explain is I will quickly create a cone. And I will use this cone. Imagine that this cone is like an arrow. Okay. And it's an arrow that it will indicate a direction. Okay. So actually, I will do different. Cone. Yeah, I will do it like this. So if I am checking this surface here, for example, and I create a cone here, right? That cone is exactly orthogonal to that surface, right? If I create another cone, for example, in this part, the direction is different, right? Because now it's orthogonal to that surface. So the normal is the direction to which the surface is kind of seeing. And this is very relevant in computer graphics, because this, for example, defines if this car, for example, is reflective. If you want to reflect this part of the car, this exactly point, right? It will reflect all the light that is seen on this direction. And this point here, it will reflect all the light, or all the objects that are actually on this direction, right? So that is the normal. And we usually compute the normal Again, the surface is, in the end, is just a collection of triangles. So we usually compute the normal by taking the cross product of two of the edges of that triangle, right? And how which order we use, the order we use to take the cross product defines if it's pointing outside the object or inside the object. Again, we will see that later also. It feels like missing a prerequisite. Something just confused. Is in the strange triangulation example, would the normal be the same for the entire quad? Will be changed by the triangulation? Very good question. Very, very good question. No, it is changed by the triangulation, of course, because quads, a quad can be planar, right? But they're usually not planar. The only primitive that is really, really, really planar is triangles. So we compute normals using the triangles. So yes, the reason that this object was seen like so weird and it had like a weird shadows, it was because the computer was computing the normals using these weird triangles because the triangulation was bad, right? So yes, exactly that. The triangulation affects the normals because the normals are computed per triangle, not per quad. Normal vectors are usually covered in multivariable calculus. I think so. Yeah, they should be. Yeah. I should write. Yes. Okay. Again, there's the math review. I am assuming that you have some previous knowledge about vectors and linear algebra in general. But in the math review, I am recommending that you could read chapter 4 and 5 from the 3D Premiere Math for computer graphics. So if after reading those chapters you still have problems, you can just send me an email and we can talk or whatever. I can maybe create more extra videos if there's something that you don't understand. Okay, perfect. So that was the vertex shader, and so let me come back. And the next section is the tessellation stage. And the tessellation stage can increase the number of geometric primitives, providing better looking models. This is, so again, let me show you what I mean with this. And I think we'll probably wrap up because we have 48 minutes already and we need to finish at 50. So yes, let's finish for now, okay? So I will explain. I have only two more slides. So basically for today, we've finished in vertex shader, okay? So tomorrow I will cover the next. And let me just quickly go to the end. So next lecture, it says pipeline. Okay, this should be pipeline. Sorry, it's a typo. So the next topic, it will still be pipeline. I recommend check Piazza, check the start. Please start your intro assignment, and you need to attend your labs. And there's this optional reading. You can read chapter 1 from OpenGL Programming Guide, the official guide to learn OpenGL. I'm already put the link on the webpage. And yeah, that's it. Is there a quiz for today? Very good question. Yes, I will post a quiz for today, later today. And also tonight, I will post the first theory assignment. That is super, super, super important, okay? You have enough time to solve the theory assignment, and I think it will not be as bad or as complicated. The quiz is not marked for correctness. Oh, sorry, I don't understand that question. I think I saw your email. What do you mean by correctness? Correctness? My audio cut off. Is there a quiz? Yes, I will post a quiz, but I will post it later today. So today, basically, I will post a quiz and theory 1. And quizzes are just for participation. Yes, only for participation, okay? There was no quiz before. The first quiz is today. Don't worry, there's only one quiz. The only assignment that you have right now is the intro assignment that is already on the webpage. There has been any other stuff, okay? Will you post it on Canvas? Yes, quiz are going to be posted on Canvas. Um, wow, this is moving very fast. Will quiz and assignment be on campus? Yes. Well, no. The assignments are on the assignment files are on the web page, and we will. You need to send your files using handing, but I think handing is not yet configured for the first assignment because yeah, we still have a lot of time ahead. Where where can I torrent the textbook? What do you mean? Are we able to do the intro before attending the first lab? I don't understand. What do you mean by that question, David? Do you mean, I mean, if you know how to do it, great. I mean, just do it, and that's perfectly fine. I mean, if I were you, even if I have, even if I solve it already, I will probably wait to the labs to see if everything is perfectly fine before sending my files, right? But yeah, if you check the assignment and you think you can solve it right now, that's perfectly fine. I think textbooks are on the website. Yes, the textbooks are on the website. Yes. You're on the waiting list. How can I attend the labs? Okay, the labs are going to be also recorded, and but yeah, it's a very good question. I will ask the. Give me a second. If you're in a waiting list, you cannot go to Piazza, right? Or can you? Can you go to Piazza if you're on the waiting list? Please tell me. You can. Okay, I think I can. Okay, great. So please post on Piazza, okay, that you're on the waiting list, and ask the TA from your lab to post the Zoom link on Piazza. Okay, so go right now. Go post it. When is the quiz due? Oh, the quiz will be probably like for 24 hours, or yeah, maybe a little bit more. Yeah. Yeah, maybe 2 days, because yeah, again, I understand you could have problems. When is the quiz? Okay, yeah. So I think we can finish for today. Thank you so much. It was really nice to have you. Great. So see you. Bye.